Okay. Okay. So welcome all to my thesis defense. Today, I will be presenting my work, which I've done during my PhD on sustainable interactive wireless stickers. So I would first like to introduce my committee members, Gregory About and Thad Stanner, who are my co-advisors, Hanju O and Josiah Hester from Georgia Tech, Shavik Das from CMU, and Joy Paradiso from MIT Media Lab. So let me start with the motivation. I'm holding a Post-it note in my hand, and we use Post-it notes in our daily lives to write text, stick it onto different surfaces to augment them with information. But sticky notes at the end of the day are passive objects. So one of the questions which I've asked in my thesis is like, what if sticky notes can do more than this? What if they had interaction sensing capability of being able to sense human gestures like speech, touch, and also provide feedback? So this is why I have built prototypes like these. And the good thing is that these are material-like, that they can have interaction sensing capability when they're augmented onto different objects and surfaces. So let's take an example of this. So let's see a conference brochure, which is embedded with the sticky note. And this could allow for having accessible input controls where people can use that as an extended microphone. Or let's take an example of a restaurant menu where people can just swipe across a food item to be able to order stuff, to create these contextualized tasks. So while we envision these standalone interactive objects, on the contrary, currently what we have and the typical interfaces which we have are constrained. Let's take example of wired interfaces. So here is a conference room microphones which are embedded in the table. So having wired interfaces requires planning. They are difficult to deploy and they're also costly. And if you've not pre-planned it, they're hard to retrofit later. On the other hand, there are battery-powered wireless interfaces, which are expensive. That when we think about scaling these kind of interaction sensing to everyday objects and surfaces, it's hard. They are limited interaction to save battery to just push buttons, and they also require maintenance. So as these interfaces are constrained, we need to redefine the system design parameters when we think about, like, for interactive stickers from just these traditional wired and battery powered wireless devices. So let's look at these one by one. So the first one is that these interactive stickers should be easy to retrofit and they should look and feel like a sticky note. So I've given some parameters in terms of areas and average thickness. Next, they should be inexpensive, that when we are thinking about being able to put it on different objects and surfaces, we should be able to scale them. So they should be approximately $1 and less in bulk cost. Next, they should be self-sustaining, and which means that once you have put it around in this environment, they should be ambiently able to harvest their power to operate. And given we have already put like some form factor and cost constraints in this ambient and like harvesting ambient energy, you possibly practically can only harvest approximately around 10 microwatts. So I've given that constraint as well. And given these constraints of form factor, cost, and power, they should still be able to do sophisticated enough functionality of being able to sense speech, movement, and touch, communicate it wirelessly, and also provide feedback. So let me come to my thesis statement. Self-sustaining, inexpensive interactive stickers can support wireless communication of speech, movement, touch interactions with feedback in indoor scenarios. So let me decouple this into these three different research questions. The first question is related to sensing. So the question is, what kind of interaction sensors are suitable for a thin, inexpensive, self-sustaining sensing system? Next question related to the communication, which says, how can a simple, inexpensive circuitry communicate interactions wirelessly, leveraging ambiently harvested power? And the third question is related to the feedback, which says, what type of display can be added to a self-sustaining, inexpensive interactive sticker to provide the user feedback about the wireless sensing? So let me go over the outline of this talk. So I've already explained some introduction where I gave the different parameters of power, cost, form factor to be balanced with functionality. I've also explained the research questions. Next, I'll be situating the work in the background and related work. And I will be progressively talking about my different research questions. The first one is sensing, and I will explain a project called Saturn and some other interaction sensors which I've developed. The next one is communication, where I'll explain about project Zeus and Mars. Both R1 and R2 I have explained in detail during the proposal, so I'll try to make it more of a review for everyone and try to focus on my research question 3, which is about display, and try to go in detail how we can make these self-powered displays. And for each of these research questions, I'll also be giving some exploratory applications which I have developed with them. And finally, I'll end with some conclusive thoughts. Okay, so let's start with background and related work. So given I already explained about the 4 different design parameters which I'm trying to optimize, power, form factor, cost, and functionality, I will be putting them in a grid-like format where my y-axis is power and the x-axis is the form factor. So in power, I have divided it into 3 parts: wired, which has the maximum amount of power; battery powered, which are medium; and self-sustainable, which are relatively lower power. The self-sustainable ones are broken even further, with below 100 microwatts are low energy harvesters, and beyond 100 microwatts, there are high energy power harvesters. And the form factor is broken into 3 parts. The first one is bulky. The middle one is partially bulky, where some parts of them are thin, lightweight, and others are still embedded in bulky format. And the last one is thin and light. So I wanted to mention that the cost in general is also a parameter, but generally more the number of power there is, more the number of components there is, and more cost. So it's implicitly embedded in this format as well, in this grid as well. So what we want to go towards is this, our North Pole is to go to the top right corner where we have the lowest amount of power which is there, but also have this material-like form factor to create these interactive stickers. So let's start with some related work. So most of the current IoT devices are wired and use battery, and they're bulky and hence not optimized for the tight constraints of interactive stickers that we defined before. And there is quite a lot of body of work related to flexible electronics, but they're not, again, optimized for the power and mostly use batteries. So next, there is work on AM backscatter that lacks taking care of the form factor seriously, or work on computational RFIDs that does not optimize on the power as much as we want due to the transistors and microcontrollers being used in the traditional saturation region. So inspired by all these work, I have built a project called Saturn, which is a flexible microphone. And I've put it in the partially mounted category because only the sensing part of it is flexible and thin, versus the rest of the circuitry, which I'm using currently, like you was using, was still, bulky. And followed by this, I have also tried to replace that in projects called Zeus and Mars, which are right now in the green region. They allow for really ultra low power wireless sensing and capability with the power, form factor, cost, which we defined before. And finally, in addition to the wireless sensing, there are work that allow for programmable displays. And inspired by that, I have built Venus, which allows for wireless sensing along with self-powered displays. So let's start with the research question 1, which is what kind of interaction sensors are suitable for a thin, low power, self-sustaining and inexpensive sensing system. And I will be talking about 3 different sensors which I've built. So the first one is Saturn. It's a thin and flexible self-powered microphone, which leverages triboelectric nanogenerator. So let me first explain you the device design for Saturn. So Saturn is built of 2 layers. One is paper, which has holes in it, and it also has copper coating at the back. Another is a layer of basically plastic. It's a fluoropolymer dielectric, and it also has a copper coating on the back. And how Saturn is built is that both the layers, like this creates a multi-layer structure, which you put together with blue dot points to create something like this, to create a flexible, thin, light microphone. And the idea is that any 2 materials, generally when they come in contact, they exchange charges. That's the property of static electricity or triboelectricity. And in this, we have tried to select two materials, which are copper and the fluoropolymer, which are as apart we could possibly find in the triboelectric series. So what happens is that as these two materials come in contact, the PTFE, usually being the dielectric, has more negative charges, which results in a generation of positive charges on the copper. So eventually what happens is that with the combination of triboelectric effect and electrostatic induction, these charges get exchanged, and as someone is speaking onto it, the sound signal or like voltage is produced. So with Saturn, I introduced the concept of self-powered sensing, where the phenomena being sensed, which is audio in this case, also provides for the power to do the sensing tasks as well. So moving forward, we have done structural optimization with Saturn, where the voltage output which we are getting from the self-powered sensor is dependent on the sigma, which is the surface charge density, and xt, which is the distance between these two layers. And we have tried to optimize them by basically different parameters, like what are the type of holes which need to be put, what are the attachment points, what's the geometry. And we've also optimized on the surface charge density by creating it, by doing plasma etching on it and making it much more rougher. So having done these design optimization in the sensor, we were able to have a performance or acoustic sensitivity of -26 dB for a normal Saturn and -10 dBs for a plasma etched Saturn. And just to put in perspective, active microphones are usually operating at like 0 to 10 dBs around acoustic sensitivity. And here is a graph where I've compared, saying, Georgia Institute of Technology with an iPhone versus the Saturn microphone, and we were able to see that approximately till 4 kilohertz, they sort of are comparable, that we are able to get most of the information out of this. So generally, when we speak, we have 90% or 85% of the information in the 4 till 4 kilohertz band. So the idea is being able to create such self-powered sensors can help us save power from like the extra amplifiers which we need to put to do the sensing. So moving forward, let me show you an example a video where I've put Saturn on an interactive soda bottle.
Let's share a Coca-Cola. Let's share a Coca-Cola.
So you were able to see that, that we are able to get audio output back. So let me now, leveraging the learnings of Saturn, I've built capacitive direction sensors using everyday thin flexible materials with simple fabrication. So using copper and Kapton tape, I've built something which basically is a capacitive sensor, which has tooths of different sizes. So as someone basically swipes across it, you could able to sense like a monotonically increasing or decreasing pattern to detect left and right gestures. And this is done with a very simple fabrication process where there's paper and a silhouette cutter is used to cut the copper foil, which are put together. And then this is basically layered with a Kapton tape on one side. And the reason it's done is like, so that there is not a, like someone swipes across it and directly touches the copper. There is a sudden capacitance change which happens, which is too harsh for the sensing, can be too, so we have tried to put one layer of copper on it, and then followed by that, each of the digits have more multiple layering of Kapton tape done to create a differential capacitance change. So having done that, we can see that we have tooths of different capacitance change, and we can use those to be able to create more different kind of patterns in terms of like a barcode kind of patterns amongst this 1, 2, 3 to able to create that, a unique pattern which is from these sensors. Okay, so let's come to the contributions from the sensing research question. So the first is that I've shown there are different type of human interaction sensing which you can do: speech, direction, and movement. Secondly, I introduced the concept of self-powered sensors, which would be useful for these interactive stickers. Thirdly, in terms of form factor, I've used thin flexible material. I've shown how we can do in-material encoding with basically the swipe sensors, but there are also interesting things which we can do in encoding the information. For example, when I was showing Saturn, which had blue dot points, changing the blue dot points can change the resonant frequency of the microphone. So, and the thirdly, that like learning to use the appropriate materials can help us tune the range of voltages which are produced or the capacitance ranges which are produced. And finally, in terms of cost, I've used easily available materials like plastic, paper, and copper to be able to build these sensors. Moving forward to wireless communication. And so in this, I will be introducing two projects, Zeus and Mars. So let me first dive in and show you basically Zeus as a prototype. So Zeus is consisting of three components. First is Saturn. And what we're trying to do is to use Zeus to be able to wirelessly communicate this information. The second is a JFET, which is a transistor. And the third is the antenna. And how this is put together is that the voltage which were produced from the Saturn goes into the gate and source of the JFET, and the drain and source output is connected to the antenna. So what happens is Saturn produces a voltage change which is across VGS, and the JFET acts like a voltage controlled resistance, which basically in the triode region. And the good thing is we are usually, when JFETs are acting in as voltage control resistors, we have a supply voltage or a bias voltage attached to it, but we are able to passively use JFET as a voltage control resistor. So it converts the VGS, which is from minus 0.6 to 0.6. So that's approximately amount of voltage which we get when we speak to Saturn, into a change in the impedance across the drain and source. So antenna sees this drain and source change of impedance, and basically that results in impedance change in the antenna. So basically what we have done is to proportionally convert the changes in the voltage into the changes in the antenna. So Zeus communicates using amplitude modulation based analog backscatter communication. So what happens is that we have a transmitter in the infrastructure which gives a high frequency carrier wave which is incident on the Zeus stack, and when there is low frequency audio which is generated because of the speech which is there is impedance changes which happen in the antenna, as I explained previously, and that results in changing in the reflection coefficient of the high frequency wave, resulting in an amplitude modulation which happens, and the receiver receives this, and we can do simple signal processing to get the speech back. So let me show you a demo where we have a transmitter and receiver, and I will be basically speaking from a few meters of distance and we can hear the received audio back.
Hello, hello. Audio from Zeus. Hello, hello. Audio from Zeus.
So we were able to hear that. Next, let me do the contributions which have been done with this project. So in terms of power, basically we have used backscatter communication, which shifts more power intensive task of generating the radio frequency to the infrastructure. Second, we have used transistors in the non-traditional way, where we have not applied a bias voltage to the transistors and being able to use them in the triode region. We have shown a sticky note-like thin form factor for the Zeus patch. And the cost of it, because it just consists of a simple circuitry which has just JFET in it, it has simple circuitry which even be printable in the future. And in terms of functionality, Zeus allows for single channel audio communication, where one tag can only operate at a time. So there are some limitations as well, even Zeus allows for some short distance of communication. So seeing these limitations as well as functionalities, I was inspired to build my next project, which is called Mars, which expands the Zeus concept for wireless communication for speech, and expands it beyond to touch, swipe, and speech input, but for multiple tags at the same time. So let me first give you a basically demo for this.
Mars stickers offer a diverse set of applications and interactions. Leveraging a thin paper microphone connected to Mars, we can enable audio or speech communication. The Mars audio tags can be embedded in a conference brochure and used as an extended microphone for central audio control, allowing the audience to ask questions to the presenter.
What are the power requirements of your prototype?
They can also be used for extending the hearing range of smart home devices to particular areas or appliances. For example, a Mars tag sticker on the refrigerator could allow a user to communicate with a faraway Alexa and update their shopping list.
Alexa, add eggs to my shopping list.
Alexa, add eggs to my shopping list.
I've added eggs to your shopping list.
Mars tags can also detect multiple discrete touch points. Powered by 2 photodiodes and leveraging inductance-based touch sensing, we create game controllers using Mars tags with 2 buttons to play the classic game of Pong. We can also show the communication of unique IDs using capacitive sensing and Mars tags powered by photodiodes. For example, a waiterless restaurant can equip its menus with unique IDs to distinguish orders. Swipe-based direction control using capacitive sensing is also possible with a Mars tag. For example, we can command a light dimmer with our tag to change its brightness.
So we have seen how Mars can enable different kind of human interaction sensing and wirelessly communicated. So let me go in some technical details of how this works. So previously, Zeus was aligned amplitude modulation based backscatter communication, while Mars allows for frequency modulated backscatter communication. So how this works is like, let's just say I have 4 Mars tags in my environment, and then there is a transmitter which is there. Once a high frequency RF wave is incident on these tags, what would happen is that each of them would communicate it back by modulating it at a different frequency channel. And the reason they are communicating at their unique frequency channels is because they have a built-in resonant oscillator, which is tuned to a unique, each of them is unique to a unique frequency. So let's see how we are able to make that unique, like make an oscillator. So that oscillator is basically a modified version of a Colpit LC oscillator, which uses a 0 threshold voltage MOSFET, which results in basically the whole circuitry consuming only hundreds of nanowatts of power. So what I mean by a 0 threshold voltage MOSFET is basically every MOSFET, when they are manufactured, have a particular, based upon their doping and how the gate and all those things are set up by the manufacturer, they can have a voltage threshold, and that's the threshold at which the gate turns on. And if that voltage threshold is lower, then the supplied voltage, which is required to the circuit, would be lower. So using this concept, we have been able to reduce the startup voltage for Mars to 380 millivolts on average, and 500 nanowatts on average for power. And this is for different oscillators, which can run till 1 megahertz. And generally, if you look at even current low power systems, they are operating at 1.8 volts and 2.1 volts. But that still requires, adding, like there is advantage to lower down power to hundreds of millivolts, and that is reflected in power harvesters. So once we have made an oscillator, we are able to add a DC power harvesters, and we have used 2 types of harvesters. The first is we have used photodiodes, which is being powered by ambient light or ambient room light. For example, this room light has approximately 500 lux of light, and thermoelectric generator, where touch of a finger is able to generate some 500 millivolts, 400 millivolts to be able to power this oscillator. And what happens is, because our oscillator has such low startup voltage, we are able to have able to affect the harvester as well, where we don't need a power management circuitry in between. The harvester is automatically impedance matched with the circuit, like the oscillator circuit as well. And because the power is so low, we can start to push it more towards small form factor of the harvesters. So having made the oscillator and power harvester, the next is to add the RF front end. We had been able to make a passive RF front end in Zeus, which was very nice, that we had speech, which was the AC wave. Here, the oscillator's output is the AC wave, which is going into my passive RF front end. Somewhere we have basically, made use of the previous Zeus circuitry and optimization, which we had done. And being able to use that, we can do wireless sensing. So basically, as I explained before, the frequency of the frequency of the Mars stack is dependent on the oscillator, which is an LC oscillator. So if we have an inductance-based sensing, or if we have an inductor or capacitor, we can put it in parallel or series with these components to be able to change its frequency. So this is how the wireless sensing is done in Mars tag in really low power. So let me come to the contributions of Mars. So the first is I have been able to show that we can do continuous simultaneously wireless sensing of speech, movement, and touch. The power required for wireless communication is less than a microwatt, which allows for ultra low startup voltage because of the zero threshold MOSFET which we have used. The form factor of it is like a sticky note, and we have been able to basically make it out of just 9 components, and we can even think of it being made printable in the future. And finally, the cost, we calculated the bulk cost for 10,000 units, which was approximately $1, and with harvest is approximately $1.4. Okay, so having made these sensors, let's come to the interaction pipeline for having made this Mars tags. Let's come to the interaction pipeline. So we know that Mars communicates to the receiver, and we saw 2 examples where we were able to also get some feedback from the user. One was basically you saw that the smart home control was able to give an audio feedback, or if we had game controllers, they were public displays which we can use for visual feedback. But that is not really enough. Like, I showed these tags to different people, and one of the first things they were like, when do we know when this is communicating or not? So it is imperative to add an in situ feedback just to even do an on and off functionality in this ticket to add more usability in the tag. So it doesn't need to be a very sophisticated display, but just an on and off functionality, which still follows our power, cost, form factor, design parameters, which we set. So for this, I have worked on the third research question, which is how do we add feedback? So why was this hard? Because we had a very stringent power constraint of approximately 10 microwatts with the what we had mentioned before for the power, cost, and functionality. Okay, so for that, I'll be explaining my next project, which is Venus. So before that, let me give you some background related work for some of the low power non-emissive displays, which might be possible, or you might have seen them being put in some low power systems before. So I'll be putting them in switching behavior and power category. So the first one is LCD. It is basically, it is generally on until the power is supplied. And the voltages it operates in is 3.3 to 5 volts. But the power which it requires for being constantly powered is not possible with the form factor and cost of the power harvester constraints which we have put in. The next option, e-ink displays, you might have seen that them in Kindle or stuff like that, are bistable, which means like once they are switched on, they'll remain on, and until a reverse voltage is applied. They are lower in power, but still the startup voltage they have is high enough that they would require complicated driving circuitry, and adding that power management circuitry also increases the cost. So even though they have been used previously in many low power systems, we can do even better. So next come the electrochromic displays. These are semi-bistable, which means they switch on, but they still have a refresh pulse, which needs to be given every 15-20 minutes, depending on the size and other factors. But the good thing is this is very encouraging because the voltage which they are being using is approximately 1 volt, and the power is 1 millijoules per centimeter square for activation. So having seen these numbers in the literature, I was really inspired that, okay, probably we can even make a device which would be able to optimize these power, these power numbers even further. And specifically because we had one of the most leading ECD groups in Georgia Tech in the chemistry department, the Reynolds group, who had been making the electrochromic devices for the last 10 years. So I basically started collaboration with them to see if we can come up with a system together which can be built into with the wireless interactive stickers. So this is where the Venus display was made, which is basically vibrant electrochromic display with nano ITO for ultra-thin sustainable systems. And the theory of operation for Venus display is basically a simple based on electrochromism, where when a change of color happens with the application of voltage due to a chemical redox reaction. So what happens is that if I have a polymer conjugate, let's just say this is an example of an ECP magenta, and in its neutral state, it is light pink in color. But as I apply voltage to it, it oxidizes, and because of loss of electrons, it becomes clear in state. And if I put a negative voltage, it basically reduces and becomes much more brighter pink in color. So having seen that, let's just look into different device design of how this device can be built. So it can be built basically with like an ECD device is basically it acts like an electrochemical cell which has 2 electrodes in it and a layer of electrolyte in between. So just general basic 12th class physics or high school physics. And the first one is a working electrode, where we have electrochemical material which is put on a transparent electrode. So for example, let me show this to you. So I have a PET sheet which is coated with ITO, and then it has a material coated on top of it. And the ideal characteristics for this is that we need to have low activation potential for the material, which means like if I'm going from one color to another, it needs to be like has low voltage. It's usually a P-type material, have simple fabrication and be stable. And the counter electrode is also a conductive transparent substrate, but it has a ion storage or a charge balancing layer. And this is a very important layer because it helps in counterbalancing the potential of the working electrode. And it is crucial for the stability and low power consumption of the EC device. And usually this is a transparent material or another type of EC material. And then there is electrolyte layer in between, which basically helps in transport of electron charges during the redox reaction. So one of the things which we have done is to optimize on the device design of the counter electrode. So the first is like generally, initially when the ECDs were built, what people were doing was putting the counter electrode to be same as the EC like electrochromic material, due to which we did not achieve high vibrant color or had high power because both of them were P-type materials. Otherwise, you can use counter image where you have a, you can see that what would these devices would change between, small, a small square which is in between and the outer window which is there. So you can see that this is how most of the electrochromic devices are built today. And then there is another way by which you can not even have an ion storage layer, but that results in fast degradation and voltage instability. So electrochromic displays, having been still an active area of research in the last 2-3 years, there has been a lot of work of how do we create a counter electrode which is transparent but can also charge balance. So basically, Dr. Reynolds' group is currently working on a new way by which they are able to use a nano ITO, which is a N-type degenerated semiconductor, which can be put very easily in with simple fabrication to allow for vibrant colors and low power and long stable life. So having optimized on the counter electrode with nano ITO, I worked on next optimizing on the electrode which should be used for the working electrode. So basically, we want to optimize and lower down the voltage as much as possible. So one of the first materials which I used was P.PSS. And P.PSS is generally used in a lot of organic flexible electronics. But as you can see, it had like onset of minus 0.8 and V clear of 0.5. And next I tried ECP magenta, which was minus 0.1 and 0.6 volt. And finally, ECP green, I wanted to say. And next, finally, I tried ECP magenta, which had minus 0.424. You might see that this is minus 0.1, but this is going from like a normal default color of green to a darker green, but that's not enough of a change to our eyes to see. So this is why we did not use ECB green, but rather chose ECB magenta going forward. So let's see how the device works. So we have been able to create a pixel, which would be able to create, like, go from a colored state to a clear state. And this is approximately 8 millimeters square and consumes basically 1.85 microjoules. So as you can see, by applying a square wave pulse, which I've done, it is changing its color from clear to colored state. So this is very encouraging because we have been able to create displays or like having to have indicators which can just start in 370 millivolts versus previously other displays or other technologies were working around like minimum 3 volts to 5 volts. So moving forward, let's see how we are able to do fabrication for Venus displays. So the preparation of the counter electrode was to be basically having nano IT on it. So it's very simple. We just basically do blade coating of it, take a pipette, put it on it, and have the blade coater run over it, creating a shiny coating on it, which is basically put in the microwave to create a device like that. And moving forward, the preparation of working electrode with having the EC material or electrochromic material is done by doing an air spray of it. First, we put a mask and then we just air spray on it. So just being able to use these simple fabrication techniques to create devices is really powerful and friendly on the cost. And then you can also clean up the ECV material to create like these hard, different type of shapes. And the assembly of the two electrode is just very simple again, that we take a separator, which is apply the electrolyte. And then on top of it, the counter electrode is placed on the two devices to create a device, something which looks like this or this. And I have another one, which is a smaller one, which is this. And someone wants to look at the prototypes, they can come later, I can show that. So once the device is built, it is UV cured and put together to be worked. Like basically now you can just use it. So Venus display or Venus pixel at this point can provide information in different ways. First is basically color. It can change from like a colored to a clear state. But then you can also use the advantage that it is going from clear and such low voltage and power that you can introduce that it can go from another color, like color A to color B, by just introducing another layer of paper below it. This is just a clever way to be able to change from one color to another without increasing its power. So this one has a layer of green color sheet, green paper attached to it. Other ways of giving, like the ways Venus pixel provides information is by, in terms of, you can create different shapes, and shapes generally can convey different kind of, small emoticons can be made or something to give different information, or you can have different shapes and sizes of the displays. So as we can see, like with different sizes, the voltage and the current and the power changes. So for example, let me just break down this chart for you. So one of the things which we notice is that the V clear, which is the voltage at which the oxidation happens, doesn't change much. It remains around 0.4 to 0.6 volts still. As the device size increases, the current also increases. For example, the 20 microampere is consumed by a 4 millimeter square device, and 100 millimeter square device consume 1 milliampere. So it certainly, like, making these devices can be like self-powered can be hard, but it is reasonable to think that we can make till approximately 40 millimeter square of devices to be able to have be operated in a self-powered way. So the same pattern is also repeated in the peak power as well. So let's look at how we can control Venus displays using different harvesters. So I've tried to basically use two harvesters. The first is the finger heat from thermoelectric generators, and second is photodiodes in an ambient room light. Before going forward, I just wanted to make some observation which can help us to create these behaviors. So there are three modes of operation for Venus. One is the off mode, which is just the default mode in which it is light pink color. And then it goes to clear mode and onset mode, which is, so these are three different colors. So there is the point to note is that there is significant color difference which happens between the off state and the clear state, which means that we can use this, like we don't need to go from onset stage to a clear stage to create an on and off display functionality. We can use this to save power or sync our behavior of changing states with the harvesters. Secondly, Venus has the behavior of a supercapacitor, which means if the Venus display is an onset on or clear, if you basically short the two electrodes, it will come back to the off state. And this becomes important because Venus generally has a semi-bistable property, and we can use this to go from, like, if we are able to short it, we can use this, leverage this later, and I'll show it how we do it. So let's see how we can control Venus with a thermoelectric generator. So this is a thermoelectric generator module, which is present. And how it operates is that there are basically PN junctions which are there. There is a heating side and a cold side. When someone touches on the heated side, it generates a potential of, let's just say, an anti-clockwise potential. And if we exchange the heated and cold side, it will generate a potential which is clockwise. So we can use this idea of being able to touch on different sides to generate different sort of potentials. So, and you can see that, you know, the output which we would get in such behavior would be something like square pulse like, and this is similar to what we had used initially to control the Venus display. So as we can see that in the onset, like let's just say the -1 sets the display in the onset mode, the positive, like the positive voltage would set it in the clear mode. Let's see how we can basically design interactions using that. So as you can see that I have connected a thermoelectric generator directly to the electrochromic display, and touching that results in making the display invisible. And there is no in-between circuitry which is attached, by the way. And it becomes clear and reveals the green color sheet which I put to show the color change. And touching at the back would result in the pink color coming back again. So being able to create such self-powered displays can also be put in different kind of applications. For example, here is an example of like having an hand touch powered interactive cards where touching on it results in creation of the heart which is there, which comes up. And similarly, touching at the back would make the heart disappear. So let's move on to the next harvester, which is the photodiodes, which is able to harvest power from the ambient light. And we can see that if the device was in the default mode, which is like light pink in color, if we had put some photodiodes in series, which basically to be able to reach the voltage potential which was required to create the V clear, which we defined, we can basically, by switching the device close, we can make it go to a clear state. But the interesting thing is, if we open the switch back again from this clear state, the pixel doesn't immediately go back into the default state. So this is where we can use the super cap behavior that we have the understanding that shorting the two electrodes can take it back. So this is why we have basically designed box-based interactions to control Venus display on and off, where the photodiode and the photodiodes is controlling the Venus display. And when it is open, then there is voltage which is applied and the device is cleared. And once the device is closed, then there is a conductive material, like there's a conductive frame which is on this box that once it is closes, it will short circuit the two devices terminals, resulting it changing its color to back to the default state and dark magenta. So let's see a video of that. So here's an indicator. Initially, it's in a closed off state. So as soon as you open, you can see it changes its color to green. And once you close it back, it will, because of the short circuiting, it changes color back to default mode. So let's see how this Venus display can be added into a wireless communication indicator. So now we have already had built the Mars circuitry, which was able to do wireless communication. So I added the circuitry back in the box together. So we have for example, the top coverlet has the antenna and Saturn and Mars circuitry, while the bottom coverlet has the photodiodes and the Venus together, and the hinge is kind of like a wired connection. When the box is closed, the device is inactive and is not communicating. Is not communicating any audio, and as well as when the device when the box is opened, then it starts to communicate the audio which is there, but also changes its color. Part of this work is done in collaboration with Youngwook, who was looking at this more from a usable privacy point of view to see how this can be extended as a microphone. So coming to the conclusion of the feedback and the contributions this research question makes. So we have been able to show that Venus is able to do vibrant color changes with on and off pixel control and provide an on and off functionality. It allows for low startup voltage of approximately 0.5 volts, allowing it to have a power of less than 10 microwatts for small pixels like displays, powered by finger heat and ambient light. In terms of form factor, it is thin and light in form factor. And because of simple fabrication and no power management circuitry, the cost of adding that to the existing circuit is also low. So having done this, let me talk about some of the future work. So Venus displays can be used as a segmented array for doing voltage level sensing, where, for example, if you have particular voltage, then only one of the devices would be on. And here we can leverage the RC circuit, or like the fact that Venus acts like a supercapacitor. We can also use it in more interesting ways, where we are using the Venus display's optical memory or the bistable property to create timers, where we have, like, initially the timer is off and there's a reference timer, and we can, it becomes clear, and eventually over time till it reaches the same state, we can, so we can have such self-powered simple circuitry timers to be put. And finally, let me do the conclusion, where, like, while building sustainable interactive stickers, I have thought about the fabrication process and device design so that we can achieve low cost, low power operation. And if we basically think more deeply, that interactive stickers do not end their operation at the end of, like, when they're operating, they also have an end of life cycle. So when we are thinking more, we need to, like, when we are thinking about having these stickers deploy in everyday environment, we need to think more deeply about what would happen to them at the end of the cycle. So currently I've been thinking more deeply about how do we dispose, like, create, how can I create a Mars circuitry or this into a more reusable, biodegradable sensor where sustainability is built in it from get-go. And let me show you an example of that, where, for example, like, initially when I had Saturn, I was making it out of plastic, and, well, paper was biodegradable, but copper. And now I'm trying to rethink about these materials and create them out of, a bioplastic, which is biodegradable, and also have, like, more benign materials, not copper, like heavy metals, but like iron in them. And finally, let's come to the research process of, like, basically what we have been able to do by adding these, like, during this whole building of sustainable interactive stickers, is that we need to be rethinking how we are going forward by these, not just taking functionality and power, like functionality and performance as the performance metrics, but also rethinking about how we can create the whole computing stack from bottom up, from device fabrication, systems, and design perspective, and going more towards sustainability. And this is a grand challenge which we as a research community can only achieve when we work on this together, where we are thinking about other type of sustainable parameters like power, waste, and cost as a metric of equal importance and success. And I would like to just summarize that I basically in this talk, I have explained how we can create sustainable interactive stickers which follow power, cost, form factor, and functionality parameters. I situated it in the related work, and then I provided progressively increasing capabilities of sensing, communication, and display, and then finally ended with a conclusion. Okay, with that, I would like to, my thesis generally has spanned a lot of different departments and engineering domains during Georgia Tech, and I would like to thank all my advisors, committee members, and collaborators who have been very inspiring and have given this so much of their time and resources. I would also like to thank all the awesome student collaborators who have put in so many hours of helping me to put together this PhD work to come to this realization. And finally, there are so many other people whom I probably cannot put name and picture, but they have all made me into the person I am. And I know a lot of them are on Zoom call right now. So thank you so much for that. Okay, so with that, I will open the floor for questions.
I think.
Okay, thank you very much, Nivedita. As we said before, what we'll do now is go through the committee. So technically, we're supposed to start with the people that are furthest away, which are usually the external members of the committee, and that would be Joe Paradisa. But Hyunju, correct me if I'm wrong. I think you're in Dubai right now. Is that correct?
That's correct.
That is correct. But you are actually the furthest away, but you're in internal examiner. So we'll still start with Joe.
Thanks, Gregory. Well, yeah, I heard you say that I would go first, so I jumped in early at the gap. So sorry for the interruption. But again, Nivedita, it's been wonderful to see this work unfold. And I went through your thesis over the last couple of days, and there's so much there. I love theses that incorporate a few different ideas, all of which are interesting, but then weave them together in interesting applications. And this one definitely does that. So bravo. I've got questions. My questions is, some of those of you who know me will delve into the details. I'll ask some of them here. But again, I think it's a really great piece of work. As we talked a little bit when we met on your proposal, yeah, when you think about how these things will scale and what's going to potentially inhibit something like this from being adopted more widely. And when you bring devices into smart environments, there's a whole lot of intelligence going on to how to join the network, how to connect, how to avoid collisions, how to work together. Matter of fact, IoT was kind of impossible until we worked all that out. Now it's almost seamless. It used to be complicated. Here, you don't have much intelligence to really do that right now, right? You're picking different frequencies for some of the devices, and we've done a lot of that, but that has trouble scaling at a certain point, or even bringing different devices together. They have to figure out, how they're going to not step on each other. So if you thought a little bit about that, maybe ways of trying to make these things interoperate. There are even standards for backscatter that are starting to be rolled into new versions of LTE or 802, whatever it is. So it may even be there in the standard now. You might be able to play with that, but I'm wondering, you're thinking about kind of how you're going to match what exists in terms of standards and how you would disambiguate different devices in a network.
Yeah, thank you so much for the question. And I think, let me answer it in this way. One of the learnings which I had during making the interactive wireless stickers is to be able to move towards circuitry, which would be really low startup voltage, and I have created some of them with Zeus and Mars, which allows for, I would say, simpler side of backscatter communication, but where I think frequency modulated are also, I would say, restricted in some sense. And if we have to go towards more complicated, avoid collisions, we probably have to basically make the circuitry a little more complicated. But still, I think the push or the learning was to go towards a little more complicated circuit, like keep the startup voltage low, have analog circuits, subthreshold level circuits. But I believe we would have to create circuits which are taking care of existing protocols more into account, even add, I would say, a layer of security or privacy in there to be able to encrypt these together, like encrypt these, what these are communicating. So I would say definitely huge future work to like look more into it in detail. But if we can keep the underlying learning of being able to use sub-threshold circuits, when I say sub-threshold, I mean like something in like hundreds of millivolts, because
So
of,
let me take Joe's question and give you a concrete example. I mean, your answer is fine, but when you look at Mars and you're using the frequency shifting,
Mhm.
how would you be able to create a set of Mars devices that would be able to Joe's point about integrating into an environment more seamlessly, they could figure out what shift key to use rather than being hard coded?
Mhm. So I think there needs to be a mechanism by which we are able to seamlessly create and be able to even see, like, for example, I have a knob almost to see like which frequency I'm tuning to, so that I can also create another software structures, or easily. I think this is where I think the power of, creating low power, but also thinking about usability and design also comes in, where we can add this some interesting user experience features where we are able to, physically see that, oh, this device is at like, 200 megahertz. And I know, for example, like the sticky note is for this functionality, and able to easily tune that in my software. So being able to create, and I know backscatter in general is limited in range in terms of how it is in the environment. There have been works which have also gone across in like different floors, like first floor to second floor, but still there are like limited number of tags, and it's an ongoing work where how do we include them with existing frequencies of like Wi-Fi is there, Bluetooth is there. So I don't have a particularly clear answer, but I think this is something which I should definitely think more about in the future. But I would say, coming back to my initial answer, I think being able to create circuitry which is really low power can all like more complicated circuitry can also allow us to create much more easier integration into existing protocols. So that is also one way to do it, or include that in the user experience itself.
Well, I have a follow-up on that then. So this is kind of looking at the committee in general too. I'm wondering if, when you're sending out the carrier, if one of the things you can do is also include some modulation of that carrier at different FM frequencies, so that you have a resonance in the tag circuits that then responds. I don't know if you thought about that at all, but actually sort of embedding in the backscatter carrier frequency the shift that you want.
What's interesting about that is you make the infrastructure more complicated, which has more computational capabilities to adjust.
There is also, I think, one more additional point. I think there is more things to be looked into millimeter, like 60 and millimeter square waves, and how we can make Mars tags more compatible to those, because I think that is where the future is going. And there's a lot of work in this domain to be able to create this interactive surfaces in those domains. So not just like limiting ourselves to Bluetooth or Wi-Fi, but also thinking about these new upcoming technologies.
Keep going, Joe.
Okay, I think actually, since your duty cycle may be very short too, maybe like infrared, it may not matter quite as much. If you're streaming any kind of a sensor value, though, then you really have to hop away, or if you go for any length of time. But this is a conversation to go on for an hour, so I think it's for future work for sure. Okay, a few other quick questions. Your capacitance strip, we talked a little bit about that. We'll talk a bit in closed session. I'll give you some other references for things that might be more robust. But the same technique though, it's a good idea. But capacitance also varies between people. When I, just try to touch my watch, I like to, work out now, and it wants me to say, log your workout, right? I'm hitting this when I'm running. It's not working because my finger's too dry. It varies between people, varies between different states of a person, right? Your finger kind of moisture and capacitance can vary. Does this change the actual, I would think it would change the frequency, the way you're doing it. It's going to, move your frequency up and down. Are you robust to that, or have you seen much of an effect? What
So
do
I
you
think one
notice?
of the, thank you for the question. One of the things, or the reason I was doing differential layering of captain, was to create enough range difference between my tooths, which is being sensed by Mars easily as like approximately 10 kilohertz of changes, which is big enough. And I would say, like, by introducing more materials, like I was using Captain, we can also use like other craft tape or other kind of plastic materials to create different thicknesses. To create, I think the idea is to create enough range out of these tooth, which are stable over different. I think I was able to do 3. Probably you can maximum stretch it out to 4. I wouldn't say you can create like 5 out of Captain and like, so I understand the limitation which you are saying, and I agree to it. Especially if I think if you're, over different temperatures and different things, there's a more deeper study to be done. I did it with like approximately 6-7 participants, where I was like, okay, 1 and 2, but are definitely like enough apart and I took it like a very big range, like each one of them should be able to create like 10 kilohertz of changes for me or something like that. But as we make this more and more narrower, for example, if I had a barcode of like, let's say I have 5 digits created, then it becomes more tricky. I would say it's easier to create longer barcode or with lesser number of digits, so that this is 1 and 0s and I'm having a longer barcode, which is more reasonable and which is more robust. But I think I was more going towards like, let me just show feasibility of these sensors being included with the wireless interaction, like with the wireless sensing. But I totally agree to what you're saying, that there is a limitation which needs to be more robustly seen in terms of like how many tooths you're able to make out of these material devices. And that's why I think one of the learnings which I'd said is like, you can choose your materials wisely to be able to tune it to the right range.
Sure.
So,
and you could do your analysis, because it may shift all the frequencies up a little bit if you're lower capacitive coupling, things like that. You can make the readout a bit more robust. But yeah, there are ways there. I'll go quick. Electrochromics. I love that idea. I love them. I've seen some great work in the HDI community coming out with those now. But your current you're pulling in the electrochromics, I think, is only in the transition, right? That thing is steady state, or do you have to always supply a current to keep it a certain color? Is it only when it changes that you apply the current? If that's the case, it's more of an energy argument, not a current argument. So you'd be talking about, microjoules, not microwatts necessarily, to change the state. And that you can basically store in a capacitor over time. So yeah, you can maybe make a bigger display, just charge a capacitor and, hit it when you're ready.
I think the idea with ECDs was in general because they're low voltage to not having a complicated driving circuitry in comparison to e-inks. And sure, I think if you can charge a capacitor and but then again, going to the voltage point, but they have bistable characteristics. Like once, for example, if it's a light pink in color, it will change into clear, and from clear it would not come back for, depending on the size. For example, if it is a bigger one, right, it will take like, I have seen 1-2 hours, and I think that there's more characterization to be done in terms of like what optical memory it provides, and that's why I added the timers.
Practically speaking, for a lot of interactive scenarios, it's bistable.
Yes.
Yeah, so
That's what I
Joe's
thought.
point is that if that's true, then you don't need to think about the power needed to drive it, but the impulse.
But that's nice with the impulse part, right? Like if I have a small
what he
interaction,
said.
which is happening, that like it kind of nicely fits in with how much amount of power we are able to generate with that small interaction with respect to what ECDs operate at. And I think that's why understanding how a device operates,
Just very quickly, it's an energy argument, not so much a power one. So it's power over time. That's what it takes to flip that.
I agree to what you're saying. Yes.
So that's all good.
And also voltage, I don't know. Small.
That's okay. A few quick questions about the acoustic pickup, and then I'm good for now. There are some things in the document. We can talk about that when we get to the closed session. How does Saturn differ from an electret, right? An electret mic, you actually store charge physically on the foil, and then as it moves, you induce charge. Here you say there's triboelectrics, but what are the layers that actually rub against each other. I think that's what you would kind of need. Or is there just charge traps? So this is just like an electret, and you're looking at induced charges that moves.
So the dielectric already has some charges, it's electrically charged, and the copper, like the paper in it is not doing anything except for mechanical support. The copper is the one which gets charges. And once you have this, then the electrostatic induction between these two layers is what is generating the voltage.
So that's an electret, Mike. That's essentially an electret. That's the function. You say triboelectric, but I don't see where you're generating static charge in this. You have charge trapped and on the foil. And as that moves, you get the induced charge. That's how an electret might works. So this is an electret geometry, which is fine. I'm not taking away from this. I was just thinking you were having a generator somehow to, the way static works by liberating electrons through friction or something. But you don't have that here. It's just trapped charge, right?
It's trapped charge, but I think generally if you generally look into the literature of triboelectric nano generators, all the devices exactly work like this, that they have trapped charge and just exchange of electrostatic.
It's also an electret mic. They make them out of FEP typically. So it's a bit of both. You're in that zone.
I also think if I can add, the electret mics generate lesser voltage output than in comparison to the triboelectric and
maybe you put more charge on it, or yours is bigger. Electret mics are much tinier. So you have to look at
that is also one of the things. I think when you're able to fabricate your own microphone, you can change its characteristics to provide what is like. So yeah,
I agree. And so that's better for you there. Your 1/d sensitivity. You say sensitivity goes with the distance between the two layers, but of course, if you go to infinity, it doesn't, because it goes to zero.
Yes.
So there's a bug there. I think it's delta d/d that you're looking at. So it's the change in distance over the distance, but that I don't think it matters too much.
Actually, I ran over it a little fast but in the paper or in the previous slide, I explained it's like actually integral of all the d's, delta d. I agree to what you're saying.
We can talk a bit either one-on-one or in the breakout. When you bend it, this is a question that puzzled me a bit, because you bend it, but you don't have too many spacers and you've got a fairly narrow gap. So I'm wondering if when you bend it, does it short? Is that a risk that happens? Or do the layers still stay apart?
The thing is, like, the copper is touching the non-coated side of the PTFE. So it is supposed to touch, in the sense like the non-coated side. So even if you bend it, it is just will touch the non-coated side of PTFE. So there is no chance of shorting. If I had touched like the other side, then there was chance of shorting. Yeah.
Okay, but if it does touch, you're not going to get the full vibration. So it's
if the copper of the other side touches the copper of this, I have done this mistake while I was building, but yes, the shorting would not result in the triboelectric, basically charge being exchanged.
Yeah, you had some nice studies on how it suspends versus the acoustic response. One last thing, it's just a comment. When you plot acoustic responses, especially for things in the audio band, but in general, you plot versus log F. Because if you look at all your plots, the ones you showed here, including your thesis, they're linear F. And that just gives me a lot of information. A lot of your spaces information doesnesn't matter. It's just this roll off at high frequency. The interesting stuff is down where we hear, which is lower. So you probably want to plot log F. I would recommend, I don't know if you have time, but it would look much more natural and much more interesting if you did.
Okay. Thank you for the comment.
Lots of other little things, but we can talk in the closed session or one-on-one. I'm fine. Surrender the witness. Go ahead.
Thank you so much for all the questions.
So I think we'll go to, see, you've got a very interesting distribution of your committee. Because Shavik at one point was, well, I think he still qualifies as internal. He's at Carnegie Mellon. So we'll let Shavik go and then Hyunju.
The hard act to follow. All right. Hey, great presentation. Can everybody hear me?
Yes.
Okay, good. My questions are going to be sort of higher level than the ones that you just answered. So the first thing I want to ask you is, what I want you to reflect a little bit on what are ways this technology is used for ill, and what can we do in design to reduce that likelihood? I have some thoughts on this of my own, but I noticed in your document you didn't really articulate this fully, but I know we've talked about it, and so I'd just be curious on your thoughts on that. So
you asked that what ill it can do is what you said, right?
Yeah, like what are the,
Yeah. So,
what-
okay.
what are the threats? What are the threats and what can we do about them?
Yes. So obviously, this is a wireless interactive mic, which could, communicate the audio out to people. So this is a audio bug, technically. But in practicality, when we start looking into how it operates and and this is also like the reason why we had, like, for example, if I have photodiodes here, right, only when there is light is when it will operate. If I had touch of a finger is only when I have that, then it will operate. So there are ways to be able to control when it is communicating or not communicating. And also one of the things is, like, when I say that this can be extended microphone for all things, and I guess, I mean, you know this, but I guess I'll articulate for everyone that we obviously have been working on this idea of like power for privacy, or like this idea of like on-demand sensors, that sensors or wireless communication only happens when there is when there is demand of it from the user. So it's very important to have transparency when the tag is communicating, and also have the user trust that when it is communicating that they're able to know that. So there has to be a match between both of them. So that is where I believe, let me go back, I guess. Not very far here. So I guess that is where we have, like, with you and Younguk, I'd been trying to see if we can, basically add the Mars tag in terms of a box where we are able to have these. So Venus display, I would say, when, adding a display is very small way to be able to add some trust that, okay, when it is on and off, but that is not full story of if the user is able to have trust on it. So what are the other ways by which we can, take away from, like, add more trust to the user that this is not an audio bug? So one of the things, and I would give credit to Younguk here, is to be able to design the box where we are able to create this disjunction, like a physical disjunction, which users are able to see. So in addition to, like, Venus display, I think solves the part, like, what display can be added in such low power to have a standalone interactive post-it note, but it is really the other kind of features which need to be added to add that knowledge and trust for the user, that when we say that the device is not communicating, it is not communicating. And I would say this is more on terms of like on device tag situation. There are also situations where I would say backscatter communication can also be bugged. What you're communicating can also be bugged. So there is need for, and I think that I'll point it to what I was saying, that having learned that, okay, we can make these really low voltage circuits, we can also think about some really low voltage hardware encryption circuits also, so that, maybe there's also a tuning switch in there in the tag itself that, you're randomizing it physically in some sense, right? Where we have taken care of being able to it not be bugged by the other people of like, so I totally agree that this can be used as a audio bug. And I believe the other sensors, like the swipe sensors or touch sensors, which are there, should, depending on where they are put or what scenario they're put. So coming to the threat models as well, something which I've learned from you and Younguk itself. So thinking about what threat model a particular scenario can offer. So for example, if I have this audio microphone in a restaurant, people would probably like have a really high threat model, or versus if I'm putting in my office, I probably need to tell people that, hey, I have this wireless interaction sticker, which is there. But so like, just like we give more notice when we are recording someone, or like, on audio or video, both. So we need to give more, we add features of notice, consent in the interaction design itself of the tag to be able to do that. I hope I answered your question in a very long way.
That was a very in-depth answer. Thank you. I have a couple of follow-ups that, some of which I won't belabor the point. So one is what you mentioned with this hardware encrypted circuit. When you're talking about these on-demand sensors, it's actually a very non-trivial problem to do public key exchanges in a trusted way. When you're talking about like having these sort of sensors that you can stick all over the place, especially pairing that with a receiver in a trusted way. That's a very non-trivial problem. So that'll be a really challenging thing to fix. I love the Powering for Privacy project, of course, as you know. However, that addresses a specific threat in the context of when the user kind of has control over the device. But there's another kind of adversarial actor here that could also be something that we need to cautiously design against. And that is somebody who, just as easy as it might be for you to stick a sticky note on your table and make that interactive or make that sort of a microphone, somebody else could do that too in a way that's like really difficult for you to notice, right? And so the question then becomes, are there strategic ways we can create design interventions to make it so that it's really difficult for an adversary to be able to do this, while still allowing it to be easy for like an authentic user to do it, right? So how would we even reason about that? And what are some of the trade-offs between, is this a good thing for the world or a bad thing for the world in light of that, right?
I think there's another thing which I would say there is a locality, and we have seen this when we were making P4P or anything, that it is literally limited to like few centimeters. There's not even a user study for me to do in some sense. Previously we were discussing during proposal that let's do 1 meter study versus that. The way we have designed it is like you literally have to speak. So if someone's literally, if I have a sticker on the table.
Well, but hold on, that's not getting at his point.
No.
Because he said you could take a sticker and put it on a surface and make it interactive for your purpose.
Yeah.
But someone else could put a sticker there also. Maybe they put it on the bottom of this and you don't notice it, but it's still within range to be able to detect. So what might you do to prevent someone else from putting something on a surface to do something that you don't want them to do?
I mean, I was following it by saying that even if you have put it right next to it, the functionality does not support the fact that it is like you have to literally put sticker near and speak, and that action itself is visible.
Yes, but what's going to happen is someone's going to improve upon your work.
Yes,
Make
I
the
agree
range
to what you're
better,
saying.
right? So you got to be careful about
Or the fact that this is a very large surface and sound travels through wood than it does through air.
Yeah.
And so you got yourself a very good vibration sensor. So,
So I'm wondering, could you think about putting something on your surface that's invisible to everyone, but says only your Post-it notes will work properly with it, someone else? So it's almost like you have to put something on a surface first for your notes to work with. Anything else is kind of neutralized.
But I'm thinking if someone else has to break that, they can even break that also, right?
Yeah, they put their.
But that's a good and cute answer to like cute solution.
then they put a second surface down, and it's the sticker surface on this.
Yeah, it's what countermeasures, countermeasures.
Yeah, I think this is
Yeah.
the thing with security and
It's
privacy,
really
right?
interesting, this notion of making something easy to deploy for anyone means that the anyone can be good or bad.
Yes,
And that's what
yes.
shopping is.
Right.
Yeah, it's vexing.
Right, and it's an important point to consider when you're making these designs, right? Because ease of use is great, but it needs to be intentional ease of use in some way. So it's challenging, but this is why threat models are really nice, because you can just say, well, we assume that the user's desk is trusted. However, an adversary like a plausible adversary could put it on the other side of your office door or something like that without you being able to notice it very easily or something. But either way, it is sort of important to think about it. Yeah. Go ahead.
I agree to what you're saying. I would like, I think, especially if I start thinking about them being used, for example, health sensing or physiological sensing, and having those kind of data is like really, like it's more of like, if you have to hack, there are so many, like even existing infrastructure and all those things, right? Like, I'm sure if someone, once they started making Wi-Fi, there would be so many that, and I'm not denying the fact that what I've created is creating privacy and usable privacy situations, but I think that also opens interesting research questions.
But I'm not a privacy fundamentalist. I'm a pragmatist. And Josiah has like an interesting framing of the question, which is how much will I pay for how much privacy will I pay for sustainability? So just thinking about those trade-offs in a conscious way, I think could be a good way for you to sort of make reasoned reasoned arguments about the utility versus intrusiveness of this cool new technology you've created. I did have some other questions, maybe slightly different here. In a lot of your demos, folks are very carefully interacting in order to make it work, right? And I wanted to ask you a little bit about sort of the reliability and the robustness of this work right now, and how much of this is like an engineering problem that like you can sort of give the specs to a team with fancier equipment and they'll be able to like make it much better, versus how much of this is like a fundamental limitation, and will we need like these very careful interactions to be doing the sort of demos that you've shown?
Good point. I think you're also saying this in terms of like we were not able to have the P4P in like real life studies, and I think and I'm saying no, I am agreeing to that, but I'm just saying like in general, like in any like especially when it is also audio, and like I was having a little more reasonably sustainable versions with the swipe sensors and all, but audio becomes more harder. But there's something in the engineering part where I think when I have this antenna and all this, till here the oscillator works really well, and something is still happening where I really feel like a proper antenna engineer needs to sit down and figure out what is happening, and I think that has not been figured out for reliability of the of the tag to be operating in as like it operates sometimes and like or like it does not operate like 100% of the times, and I'm saying like okay, like at least for the CCs I'm saying like okay, 80% feasibility happens and like this is possible, but I believe there is more engineering to be done for reliability, and and I'm not going to say I'm equipped enough for it, in the sense that I think more from like system perspective. Let's put these things together, show feasibility, think about from materials design perspective all together, and good point. Good point, as I would say, and probably once I become a professor, assistant professor, I can get more students to work on that. So
to be clear, it's really hard.
Yeah, I mean, is it something that you would have a research student work on because there are breakthroughs that need to be happened, discoveries that need to happen, or are they just a matter of taking what's already known? I mean, what's impressive about your work is you've demonstrated lots of different kinds of skills, but you're not the master of all of these skills.
Yes.
If you had masters in all these skills, would Saturn, Zeus, Mars be much better than it is right now? So it's not something that a researcher needs to improve upon.
I think I'll come back to the backscatter, or like I think as a technology, like really the only backscatter technology which has scaled is like RFID IDs, right? Like literally take them, put them next to each other. There is still in the last, I would say 5 to 10, since like I'm at least still ambient backscatter was meant. There has been progress, but I don't think we have like from the first prototype which was made till like last 6-7 years back, we have made tremendous progress in terms of like more robustness, more types of frequencies to be used, more things. I would probably say like there are probably more things to be discovered to be making them more robust in the way and usable in the way and scalable in the way that backscatter technology. When I say like in this room, I put backscatter technology, like each tag is going to work. It is definitely like going to work, all the time. It is still like literally, I think I was at Mobis's and there were people were saying like, oh, tag position is getting changed and this, that, and our tags work, right? Like, but when someone showed existence proof 7 years back, it was not there. So I think looking more into, there are probably, I think the answer is yes, there are more technology path picking things which need to be done.
Any more questions, Shop?
I have one more, and then I'll give up the pulpit. So in slide 52, this is when you alluded to a human-centered design exploration, and that put you into this trajectory to have feedback. I'm curious if you did that more generally. Have you done human-centered design explorations of like what people actually want out of these tags? And if you have, could you reflect on like what are the future of these tags? What are the application areas that people are actually excited about with respect to having these sort of self-powered sticker interfaces?
I thought Hanju was gonna ask this question, but you did.
Sorry, Hanju.
No. No, sorry, I just, So, okay, the true answer is no. I think I was more focused on trying to just get this display working and showing that, okay, feasibility or like selecting the right display, putting it all together. But I think one of the things which I agree that I should be doing is actually showing this to people and say like, okay, this is a display, and probably I'm able to power not just, and I think with, at least for P4P, I become a little more liberal with the photodiodes, right? But from 2 I was like, okay, that is not the main aim. Like, I can add few more photodiodes to add more functionality in it, and I'm okay with that. Versus once I open up domain and say like, okay, put more like enough constraints that it is not like completely taking a lot of power, but enough power. I think I would love to do a user study and usability study about it in terms of like understanding, does adding a, like, one is like looking into adding a display from a privacy perspective, right? Then there is another thing like how much usability it increases for the users. And but in general, I think people just swiping and just getting feedback versus having something light up and not do that. I think there is a user study to be done there. I agree.
Hey, sorry, I couldn't hear. It sounded like somebody was saying something, but I will give the floor to Hyunju, I think is after me.
Go on, Hyunju.
Thank you. Hi.
Hi.
Great work.
Thank you so
Needless to say, it's fantastic work, and I'm a big fan of your work.
Thank you.
I was thinking to start from higher level of question, but actually just let's start from the last question Shavik just wrote. Your user group, who are your users in your mind?
So, okay. I think that depends on application, for example, right? Like, let's just say I had a self-powered interactive card. I would rather have kids do it, right? But I think there the argument would be still that, okay, can I make things in such low power and like low cost is where that functionality would shine, right? Like if I've given, like, kids are like later part of it, but the reason I would be doing is like more democratization of simple fabricated devices, which is there. Or if I'm having a smart home control things, then I would probably say everyday users who are there. Or if I put something similar in old age homes, then I'm just giving example. I think depends from application scenario to another of like where, or even if I have a health sensor, which is also showing like, okay, I'm communicating right now, or like if I want to have a press a button and just show, and I think that's the answer, user-centered design.
So let me riff off that, because I think there's a completely different user population. This is going to sound odd, but I think your users are the computing industry. Because what you're trying to do.
Computing industry?
Yes, you're trying to demonstrate to people who produce interactive objects that they can and should do this by keeping other parameters in mind. Keep the cost down. Keep them sustainable with respect to power. Keep them the form factor. Whatever kind of consumer capability you're going to provide, do it in such a way that those things are held true. So in some sense, what your thesis is all about is that it's possible to do this, to create increasingly interesting functional capabilities, but still maintain those strict requirements of how you phrase it. What I usually say is the power, cost, and form factor, scale and form factor. So
that's an interesting thought. I didn't think like that, but
because now what you're doing is you're giving people like Hyunju the idea that, okay, I can create something that ultimately will be a little more thinner, more flexible, but it has input and output capabilities.
Yes.
Where would this be most interesting? What kinds of material properties should this have? And then she can go off and get people to think about what would they like tables to do or shirts.
Okay, I think that's a good point. I understand what you're saying, and I think my job should be able to create toolkits in some sense, so that I can give to designers like you who can also figure out further more human-centered solutions and applications where something like this should be useful. And I think that's a better answer.
Thanks for the clarification. We can talk more about this later. All right. I think it's kind of connected question, but I want to kind of reframe this question from your motivation angle, because you started with the very strong motivation. You wanted to kind of add intelligence. That's how I understood adding intelligence to sticky notes. So now looking back, in your view, how close are we now in your goal of making a computational sticky note? Especially in terms of the form factor, look and feel of sticky note. Are we done or
No,
not there
we are
yet?
nowhere not done. We are nowhere done.
If we are not done yet, what are you? What?
Which design? Oh, the first. Okay,
Yeah.
let me.
Sorry, Joe, just your.
Of course,
question
no. I
reminded me
wanted
of
to
that.
hear since you said we are not there yet at all. I want to hear what do you think would be kind of missing pieces?
Because I think you oversold at least Mars with respect to thin and light.
Yes.
Yeah, so push it over to the left. It's partially bulky, if I understand what partially bulky means.
Okay.
It has a bunch of traditional,
Yes.
hard.
Yes.
Dimensions. Yeah.
It's Joe's raisin bread.
Right, exactly. Yeah.
Okay, agreed. In the sense that, okay, let me come to, for example, these inductors and all can be, made much more thinner. Inductors are there, get an antenna engineer, they'll make you a millihenry inductor, for example, right? Photodiodes, there are much more thinner photodiodes which are there. I think mainly what comes down to is like, how do you create the zero threshold MOSFET, which is thin, that it can be, paper, like, can be material like, and that's like whole big engineering task in itself. Like you probably have to give it to a material science PhD student, I would say, for 2-3 years to be able for him to build a zero threshold MOSFET. And also, even if he or she is able to build it, then making sure that the power is low. And also, like, if we start adding more sustainability measure, not just power, like more biodegradable substrate and all those things. So those start to make things more and more complicated. So if I had to say, like, how close am I to make a biodegradable sticky note, I would say easily 5 to 10
Months.
Saturn is 5 months away. Okay, for example, Saturn is 5 months away, and that's why I started with the simplest one. Okay, like let's take, which is like Saturn also like thin and flexible, but when I start adding biodegradable one. But and I think one of the things is to be able to inspire other people, I would say. Like,
well, so that's where I think this chart is interesting, but doesn't go far enough. On the Y dimension, you give measures of power and energy there. So it's clear how one can say that how you can be better.
Yeah.
Right. But and this is where Hyunju and material scientists would come in to say, let's take that X dimension and make that something that's more, it may be multiple dimensions, but let's just take the thinness or flexible nature of it. That is something that you can quantify to say, to what extent can Mars be improved to be more like what a Post-it note is like from what the current prototype is, so that because I think you have a thesis that will inspire lots of people. And so the goal for you now is to say, where next? Once you've done the biodegradable version of Saturn, what comes after that?
We can have displays which are biodegradable. I'm just telling you, as simple as like there are existing proofs of cellulose-based displays, but I think the idea is like currently biodegradable transistors are like in very, very nascent stage where they're basically just starting to be built, and you have to put it in a glove box and make it remain there. So
so half-life or what the dissolving agent needs to be. So I think we sometimes try too hard to say that what we've done is all the way at the end, as opposed to saying, I'm just taking you further than has been, I pushed the frontier, but there's more of a frontier beyond that. So particularly when you're presenting this in faculty talks, you want to tell people there's a long way you can go with this.
Yes,
when you're talking to students to motivate them. I've done a lot, but boy, there's so much more you can do.
Yeah. I totally agree to what you're saying. This is a little overselling, but I think one of the points that I wanted to the reason out is like, flexible electronics is great. It has more of seeing things from a form factor perspective, but they are still putting like batteries in it. And I think if we are going towards this vision of low power sustainability, then we need to rethink how we are even making our flexible electronics. And the way I've been designing things sort of starts to touch that, or like this is where I was putting flexible electronics in partially bulky. But I also think like, yes, mine is also not completely thin and light because it, yeah, I took all points taken yet. Hanju was asking some separate question initially, right?
I mean, yeah, sure. I mean, but I just want to add, when you talk about, when you started with that strong motivation, you know, the sticky note like computational material, properties I thought of included, you know, things that I can kind of tear out, crumble, fold it, like what I often do with sticky notes. So it'll be interesting to hear your thoughts, you know, maybe later, you know, what kinds of things will be needed, how long this will take further, you know, to be able to get there and let people like me, you know, use materials just like what we do with sticky note. That's kind of the question I want you to kind of drive in.
No, I think this is a very question in general. And I think that's where I started to do with the biodegradable satin that, okay, let's just crumble it and put it in the waste bin, or just be able to put it in soil where it can degrade. But I think other components, even if it's Zeus, which has just one component and other things can be made, would take some time, I would say. Like you can have like a mixture of like reuse.
The way you presented your whole work is, you know, the material framing, not like a product, right? So when you say things like, you know, things as material, in front of designers like me, you know, what we think of is, you know, having the agency, you know, being able to modify, being able to use it to make something.
I agree to it. I think adding one slide at the end saying like, hey, this is where it is, and you know, this is where it could possibly go, and that requires more work. I think that would have at least closed the loop to save me from this question. And I think I see why you're bringing it up, because that probably can be asked further when I present my work. So yes, very important point. Yeah, take it.
All right. Thank you. Then I would just add last question. It's really about, you know, contribution, and there's no question about, you know, how much contribution you have made out of this whole work. But I want to drive this question kind of to let you describe that once again. Now, stepping back, thinking of Saturn, what is that, Mars, Zeus, Venus, all of them are amazing creations. And at the same time, we all know, you know, the field keeps growing, and some smart people will soon perhaps, you know, further advance the field and invent maybe cheaper and cleaner and self-powered, you know, technologies. Then having that in your mind, what are the takeaways from this work? What do you wish to be the overarching, you know, timeless contribution to the field and the world?
Let me take a minute on that.
10 years from now, what are they going to say about your work? Other than that.
I think one of the important things in this work is, you know, people have taken form factor, for example, flexible electronics seriously, or there are people who have taken low power seriously more, or, you know, but I think taking power, cost, form factor together to be able to create, so I wouldn't say it's sophisticated, but enough functionality that it can be used for interaction sensing or like usable uses, almost had to take like, you know, balance of a lot of things together, right? And I think pushing forward that vision that, you know, and that's what I was trying to sort of allude in the end, that, you know, when we think about creating these computing for the next 10, 20 years, we don't need to really just think about performance and functionality only, but think in other domains to be able to push and rethink how we have been creating computing till now, and also as a research community, consider that as success is what I would say is the biggest takeaway, if I have to say.
Did you satisfied?
I don't know.
Yeah, I think you can say some more about it, especially given you recently wrote really exciting paper and got an award out of the original paper. But yeah, let's move on. I'm
Okay,
fine
okay.
with that.
We'll move on to Josiah.
Okay,
Yeah, okay, I mean, thankfully people have asked some of my questions, so I'll try and keep it to two. Really hard, and we can always talk later. Can y'all hear me on the Zoom?
yes, the owl is
Yeah.
really good.
Okay, oh, cool, awesome. So I guess the first one is Joe kind of talked about it, this idea, I mean, from what I got from Joe's question was this, which is similar to what I'm gonna ask, there's this computational or intelligence overhead to being a good citizen as a device of some larger network. Like,
Mhm.
we're just integrating in some way, like using existing paradigms. And even if we have some new paradigm, there's still gonna be some intelligence cost. And intelligence means power cost.
Yes,
So at some point, you'll have to pay this fine,
yes,
right? And
yes.
so I guess my big question around that and kind of what I was thinking about is, you know, in this, and actually, this was the slide I was thinking of too.
Yes.
In this, you're talking about power and form factor, and power is on the slide is kind of a stand-in for computational capability.
Yes,
Like,
yes.
how do you think about that third axis, maybe that's going in Z of like
Yeah.
computational ability, and what's the roadmap for adding computational ability, inference? I mean, you got an ML and intelligent systems PhD, right? Like, what is the computational roadmap now that you've laid some wonderful foundations on kind of the intersection of materials and design and interaction? And that is the question. And tell me so I can write
I
a
think-
proposal about.
Okay, I think the computational in terms of like, there are two parts, right, to computation. One is like, let's add more in-device learning. For example, what intermittent computing does in terms of like, you know, being able to use microcontrollers to do those things. And
Do you think we should integrate microcontrollers into this? Or
no, that let me finish the thought. Like, then it or that is one part. And then there is another part is like, how do you communicate with infrastructure? The cost of power for that, you know, like how do you make it coherent with the whatever protocol you're using? I think those have different computation timelines. First of all, that was the point I was trying to say. So when you say computation, let's define what which type of computation we would be wanting to talk about, right? Let me talk about, because you asked, should we add microcontrollers? I think not. I mean, I think you know my love for neuromorphic computing, and where I think that we need to be able to, you know, think about really low power analog computing, or even think about how materials and their device structures are able to can have computation in them. And somewhat Dink's thesis was able to add that idea of like, you know, computational photodetectors in that, to be able to lower the power by including these interesting ways, either in a device structure or, like I would say, creating some really interesting low power analog computing circuits. If you want to do on-device computation, I would say don't go digital because that's costly. And there is still, I would say, upcoming, even microcontrollers are A to D right now. Obviously, they are as in like hybrid analog and not A to D, but hybrid analog and digital right now. So, and like Ambik and all those are also doing some really low sub-threshold as well. And I think they're already going in that direction. So I'm not going to say like, and I think there probably are still working throughout, like they're still using normal transistors. I would say even go lower in sub-threshold regions to lower that out. But at some point, you probably have to add some digital with how world works in it. But I would say minimally add that. So I would believe that most of your signal processing and all those machine learning could be done in neuromorphic computing. Even I would say create intermittent computing circuits, given like intermittent computing for other people allows you to have unreliable. But I think how would you add checkpoints, right? For example, if I'm creating checkpoints in analog, that's whole another question in itself. But this is where I would say I haven't thought this through properly, but I'm just, but so those things are there. That's one part of computing. And then there is another part where I think, how do you make it compliant to other network? And that adds cost. I think at this point, it's more of like, I think obviously people have used like Wi-Fi to be able to like, Wi-Fi is initially when like around 20 years when Thad was in his PhD, there was not Wi-Fi everywhere, right? And they were putting these like, they were doing GPS and all that, but we can imagine a future where Wi-Fi is already there. I think as a community, when we are pushing for sustainability, we need to come up with these protocols also and say like, hey, our sensors are working in this better, or like, it's just not about creating the IoT device, it's also about creating the above network layering, which needs to be put from a sustainability first perspective. I think this is something similar which is happening with the data centers also. For example, it's only in the last 5 years or where the carbon, like, and I'm not saying I have answers to these things or like roadmap completely, but I think there is need for not just when like if we as system researchers or device people are able creating things from scratch, from materials to up, there is people who should be coming in network layer and like what's the cost of adding that? And I'm hoping that if we are able to create more sustainably pro protocol, then more people would be able to adopt it in the next 15 to 20 years, that it would be as prevalent as Wi-Fi. And I think that's where all the companies and all these other people also come in. I don't think I gave you a roadmap, but answered something.
Well, that's hard. I mean, well, I guess you kind of answered it in terms of the infrastructure side, like, do I really want to integrate with Wi-Fi when Wi-Fi was made with completely different design requirements and thoughts, and it's kind of even not that great now.
Yes.
It was power intensive. Maybe you're thinking or should be thinking more like, all right, what's the next BLE plus gonna
Yes,
look like?
yes,
How can my devices inform that protocol? Right, like how Colleen Josephson, right, when she had a talk with your NSYS about Green Software Foundation and how they're trying to advocate for rethinking of these protocols. And maybe that's the better path for the infrastructure, so you can lower that overhead. That's what I got from what you said. For the microcontrollers, I have no idea. I think the neuromorphic is really interesting. I would love to understand, what are the, I guess that's kind of what ties into the second question of how you talked about shifting, like to make Mars work, or yes, Mars work, you're talking about shifting some things onto infrastructure, which is a backscatter type trick, right? But what's the cost, I guess, of that
Yes.
sustainability wise?
Yeah, I agree to what you're
Use more power.
Yes,
in
I
infrastructure.
constantly. Or I think this is where you like, at least just to answer to people, I'm like, oh, infrastructure already has Wi-Fi, so this can be ported from 915, which is a UHF band, to a Wi-Fi band. But I guess there is still the question of like, what's a sustainable network protocol? Or like, even if I'm creating a sustainable network protocol, I think that's the talk which you were sharing, right? All the privacy cost also comes in. It's not just like power cost which comes in, privacy cost also comes in. So privacy is also a sustainability question at this point. So I think thinking on those lines that
There's lots of dimensions. So think about convenience as well. So if you could do reliable body scale backscatter to your phone, then the convenience argument is I have only one power supply that I have to maintain. Now, then the question is, do I end up using more with that power supply than I would have without? My guess is initially yes. So then you have to think about how can I make that even smarter. But there's so many different dimensions that you can design for.
Yeah.
Whether you're making things convenient, whether you're making things, the things that you deploy, lower power or cheaper, where is the intelligence?
Well, that's such.
I think if whatever dimension I covered, there'll be something which will be left and people will come and say.
Well, that's right. You've got a never ending
Yeah.
agenda here.
This is what's called job security.
Yeah.
I mean, that's the convenience argument of like, yeah, if I have a phone, but then I have 10 chargers in my home, and those are all incredibly inefficient, either wired or wireless. So now I'm constantly, they're drawing power when they're plugged in, even if they're not connected.
Yes, yes, yes,
Whereas a wireless, if it's just a single one that's hooked up to a green leads building. Actually, that might be less, right, for RFID, so that's,
yeah.
it's a really. And how do you fix that? You don't. How do you fix that? But I get, okay, I move on to the last question.
No, I'm also thinking finally.
These are great, and the work is amazing, obviously, I'm a huge fan.
Thank you,
it's
thank
super
you.
cool, super fun, I also just love working with you, it's been a great time being.
Same here.
It's been really awesome, and connecting with all the wonderful committee members.
Oh, come on, get on to that.
So Venus is really cool, and you have, from my mind, you have this really nice, low power, low cost, low size, sustainable mechanism that basically converts electrical signals into photons, right? That's the definition. Electrical signals into photons, light of some type.
Yeah, yeah.
right?
Color
And that's
change.
electrochromatism
Yeah.
in a basic sense. So, and the way you took advantage of it, which is very interaction based and UV-Conf, was I'm gonna make interactive things.
Yes.
And at least from my perspective, like the interactive things were the least interesting. Because you could maybe make like why do you have to constrain yourself to pixels that must be visible to the human eye? When you said that the green pixels have lower energy cost, but you couldn't see them, I was like, oh my gosh, that's a perfect visual light communication protocol or readout circuit or memory. So are there, if you like kind of detach Venus from it has to be interactive and then think about how it could replace computing components, for example, memory, we're talking about neuromorphic and memory computing, where does that lead you?
I think this is where I was leading to, like timers that you can have an optical memory out of it. And actually, I think that's where things become more interesting, right? If basically this is like future work need to characterize this optical bistability more to be able to create these other type of circuits, or like I think one of the things which Venus does is it's like a super cap, right? And then think about using it in an intermittent computing circuit to be able to see, like, you know, I know you're thinking that to be you're wanting me to answer that. So to be able to see, like, you know, one of the things which intermittent computing circuits do is to have the capacitor charge up and then discharge out, right? And if I have a real capacitor and I have a smaller capacitor, you know, just to see how, if it is charged or not, to be able to, not for interaction sensing, but more from informing the user about the health of different things, right? And this is the same idea which I think we are trying to build more on by using microbial fuel cells along with the Venus to be able to see, you know, is my voltage enough or not? And this is where I think segmented display also come in, that okay, I have underused Venus right now. I agree. I agree to it. And this is where it's not a full paper right now, but being able to add these more interesting application scenarios would act, and also more characterization in terms of like how, like, you know, what's the voltage which I'm able to sense with these pixels to be able to like do these other applications. Or like I have also seen, like in general, I was thinking that if it's a super cap, it's also capacitively touching, right? Like those are other things which I can be using it for. It's a capacitive sensor. I think I got that idea out of, I think, someone using e-ink display as a capacitive sensor. And I was like, I didn't think so. And so I think there are more ways in which just a pixel, like right now I'm only showing it like, you know, proof of concept, this is how it works, this is how it fits into the system, but there are other application scenarios where it is applicable, given we are like, I think one of the things with these material devices is like, you know, given we are just like, you know, raw out of the market, like out of the research lab able to get them, we can, as application researchers or system researchers, whatever to call it, think about these interesting application scenarios in which we can be able to put these things. So totally buy what you're saying.
But I challenge you to think about this device and it's what I think is its most basic form, which is it's a single bit of memory storage.
Yes.
And so how can you use that? It holds information and then that information goes away after some time.
Yes.
And so all the other parameters you can change. You can make it visible, invisible. A infrared can read the invisible portion. It doesn't have to be eyes. Right. So from that very simple definition,
why would you need it through infrared? Because it's like goes from clear.
So if I wanted to like transmit or read data off of it, and I wanted really tiny pixels, and it didn't have to be usable, or it's viewable by the human eye, but very tiny pixels and a different color that can't be seen by human eye, that still has information encoded on it. And so I could just shine a light at the reflection and pull back that information off. So you could maybe put that into like robotic skin that detects strain and it kind of embeds the strain and movement, changes the pixel color, and then you can read those invisible pixels off.
I think you're basically trying to say something like a other readout mechanism, just like, backscatter does infrastructure putting things, and I think I see that.
Like
Someone would come back to me with
register
power
change.
argument on that.
Yeah, I mean, you can register a change and then you can.
Yeah,
That's what I think
no, that's a,
That's it, I see mine.
no, that's a good one, yeah.
Yeah, go on, Ed.
So one of the nice things about the thermoelectric generator that we said for, the audio system
Mhm.
was that eventually you'll get the heat differential being nothing as the other side heats up.
Yes, yes,
And so that makes it great because from a privacy standpoint, right? Yes, it works for 30 seconds or so, but only worked for so long. So even if somebody wanted to, heat up a distance or something, it's only so long. As it works. But now you've connected it up to Venus,
yes.
which is basically a supercapacitor, as you said. So let's do the situation where I am using the thermal.
It's a very bad supercapacitor, it's a supercapacitor, just the same. It's
So-
like a supercapacitor.
I have now used the power on the thermal generator and I'm powering my microphone just fine. And I've switched the state of the display.
Mhm.
So I know that's happening. What happens when the thermal generator equalizes? What does the display do?
So the display would remain switched on for some time.
Is that the problem?
That is why the box interaction was there.
Well, I'm saying that's the box interaction, that the box interaction.
It was
there.
photodiodes.
Right.
I haven't made a thermoelectric version of Mars and Venus together. Let me think this out right now.
How fast does the display leak charge?
Oh, that depends on the size. If I have a bigger one, it would go for a few hours. If it's a smaller one, few minutes. If it's a very tiny dot one, it could actually be within like,
So you could actually fix this problem just
By
by
making-
making a display that's equivalent to the size.
Yep.
Okay, that solves my question. I'm done.
I asked all my questions during. to Prolong that, but
Is this someone asking questions?
are there any questions?
I don't know. I haven't seen chat.
Any questions from the peanut gallery, folks here?
Only 16 participants.
We are at a little after 2, and we have hard stop at 3, so it'd be good if we could go to the kind of private
Mhm.
section. Could you turn off the recording?
Yes.
And if there are any Georgia Tech faculty other than committee members, you can stay. I don't actually see any other than committee members.
Okay, one second.
I'm gonna take a quick bio break and then we will
Let me see how I can.
reconvene. Can we move the little video cube to be in?
1 second, let me
huddle.
see. Is it still recording? Yeah, sorry.